What if the universe began not with a single event, but with a symphony of cosmic forces we're only beginning to understand? Picture this. Over 13 billion years ago, the first galaxies emerged from a sea of darkness, their light traveling across unimaginable distances to reach us today. These ancient structures hold secrets about the origins of everything we know, stars, planets, and even life itself. But how did they form? What forces shaped them? And what can they tell us about the universe's earliest moments? In this video, we're diving into 30 groundbreaking theories about the universe's first galaxies. From the explosive birth of the cosmos to the mysterious role of dark matter, we'll explore the ideas that scientists believe could explain how these cosmic giants came to be. Each theory is a piece of a puzzle, revealing a little more about the universe's grand design. So if you've ever looked up at the night sky and wondered how it all began, you're in the right place. By the end of this journey, you'll not only have a deeper understanding of the universe's first galaxies, but also a newfound appreciation for the sheer scale and mystery of the cosmos. Stay with us, because what you're about to discover might just change the way you see the stars forever. Now let's step back to the very beginning, the Big Bang. This monumental event didn't just mark the birth of our universe, it laid the foundation for everything we see today, including the first galaxies. Imagine a universe smaller than a single atom, suddenly expanding faster than the speed of light. In less than a second, space itself stretched and energy began to cool, forming the first particles of matter. Over the next few 100 million years, these particles clumped together, pulled by gravity, and set the stage for the first galaxies to emerge. But here's where it gets even more fascinating. The Big Bang didn't just create matter. It also left behind two mysterious forces that would shape the universe's destiny: dark matter and dark energy. Dark matter, invisible and undetectable by conventional means, acted like a cosmic scaffold, pulling matter into dense regions that would eventually become galaxies. Meanwhile, dark energy, a mysterious force driving the universe's expansion, ensured that these structures had the space to grow and evolve. The timeline of these events is staggering. Within the first few minutes after the Big Bang, the universe cooled enough for protons and neutrons to form. Over the next few 100,000 years, electrons joined them, creating the first atoms. Then, as the universe continued to expand and cool, these atoms began to gather in clouds of gas, setting the stage for the first stars and galaxies to ignite. It's a story of cosmic patience, where even the smallest particles played a role in building the universe we know today. So, when we look at the night sky, we're not just seeing stars and galaxies, we're witnessing the legacy of the Big Bang, a story written in light and shadow, matter and energy, stretching back over 13 billion years. And as we explore the next theories, we'll see how this incredible beginning set the stage for the universe's first galaxies to take shape. Now, let's shift our gaze to the next chapter in this cosmic story: the role of primordial gas clouds. After the Big Bang, the universe was a swirling sea of hydrogen and helium, the simplest and most abundant elements. These gases, known as primordial gas, were the raw materials from which the first galaxies would eventually form. But how did these diffuse clouds of gas transform into the intricate structures we see today? The answer lies in one of the universe's most fundamental forces: gravity. Gravity, the invisible hand that shapes the cosmos, began to pull these gas clouds together. Over millions of years, regions of slightly denser gas started to collapse under their own weight. As these clouds grew denser, they began to heat up, creating the perfect conditions for the birth of the first stars. These stars, in turn, would light up the darkness, igniting the process of galaxy formation. But it wasn't just gravity doing the work. The universe was still expanding, and the interplay between gravity pulling matter together and dark energy pushing space apart created a delicate balance. In regions where gravity won out, gas clouds continued to collapse, forming the seeds of the first galaxies. These early structures were likely small and irregular, but they were the building blocks of the grand cosmic architecture we see today. What's truly remarkable is how these primordial gas clouds set the stage for everything that followed. The first stars that formed within them were unlike anything we see today, massive, hot, and short-lived. When these stars died in spectacular supernova, they scattered heavier elements like carbon and oxygen into the surrounding gas, enriching it for future generations of stars and galaxies. This cycle of birth, death, and rebirth would continue, shaping the universe into the complex and beautiful tapestry we observe now. So when we look at the night sky, we're not just seeing stars and galaxies, we're witnessing the legacy of those ancient gas clouds, the cosmic cradles that gave birth to the first structures in the universe. And as we explore further, we'll see how these early galaxies evolved, merging and growing into the vast cosmic web that connects everything in the universe. Now, let's turn our attention to the stars that lit up the early universe population, 3 stars. These were the very first stars to form, and they were unlike anything we see in the cosmos today. Born from the collapse of those primordial gas clouds we just discussed, population 3 stars were massive, incredibly hot, and burned through their fuel at an astonishing rate. Their lives were short but spectacular, and their deaths played a crucial role in shaping the galaxies that followed. Imagine a universe still in its infancy, dark and filled with nothing but hydrogen and helium. As gravity pulled these gases together, the first stars began to ignite. Population 3 stars were giants, hundreds of times more massive than our Sun, and their intense heat and light began to ionize the surrounding gas, carving out the first pockets of structure in the universe. But their brilliance came at a cost. These stars lived fast and died young, exploding in colossal supernova after just a few million years. These supernovae were more than just cosmic fireworks. When population 3 stars exploded, they scattered heavier elements like carbon, oxygen, and iron into the surrounding gas. This process, known as chemical enrichment, was a game changer. For the first time, the universe had the building blocks for planets, complex molecules, and even life. These heavier elements also helped cool the gas clouds, making it easier for new stars and galaxies to form. In a way, the death of these first stars paved the way for the birth of everything that came after. But population 3 stars didn't just leave behind a legacy of elements, they also played a key role in shaping the early universe's structure. The energy from their supernova created shock waves that pushed gas around, triggering the collapse of new clouds and the formation of new stars. This cycle of creation and destruction set the stage for the first galaxies, which began to take shape as these enriched gas clouds continued to collapse and merge. Today, population 3 stars are long gone, but their impact is still felt across the cosmos. Every star, planet, and galaxy we see owes its existence in part to these ancient giants. They were the pioneers of the universe, lighting the way for the intricate structures that would follow. And as we continue to explore the cosmos, we're uncovering more clues about these elusive stars, piecing together the story of how they shaped the universe we call home. Next, we'll dive into another pivotal moment in cosmic history, the epoch of reionization, when the first galaxies began to illuminate the universe on a grand scale. Now, let's step into a transformative era of the universe, the epoch of reionization. This was a time when the first galaxies began to shine brightly enough to fundamentally change the cosmos around them. Picture the universe as a vast, dark ocean of neutral hydrogen gas stretching across the void. Then, like lighthouses piercing through the fog, the first galaxies started to emit intense ultraviolet light, ionizing the hydrogen around them and turning it into a sea of charged particles. This process didn't happen overnight. Over hundreds of millions of years, the light from these early galaxies gradually broke apart the neutral hydrogen atoms, stripping away their electrons and creating a universe filled with ionized gas. This was cosmic reionization, and it marked a turning point in the history of the universe. Before this, the cosmos was opaque, with light unable to travel far without being absorbed by hydrogen. But as reionization progressed, the universe became transparent, allowing light to travel freely across vast distances for the first time. The energy driving this transformation came from the first stars and galaxies, particularly those massive population 3 stars we discussed earlier. Their intense radiation was the spark that ignited the reionization process, but it was the collective light from countless galaxies that carried it forward. As these galaxies grew and merged, their combined light continued to ionize the surrounding gas, carving out bubbles of transparency in the cosmic fog. But reionization wasn't just about clearing the way for light. It also played a crucial role in shaping the structure of the universe. The ionized gas became hotter and more energetic, which influenced how galaxies formed and evolved. It also affected the way matter clumped together, setting the stage for the large-scale structures we see today, like galaxy clusters and filaments. In a sense, reionization was the universe's way of turning on the lights and setting the scene for everything that followed. Today, we can still see the echoes of this cosmic transformation. The light from the most distant galaxies carries clues about the reionization era, helping us piece together how and when it happened. By studying these ancient signals, astronomers are uncovering the story of how the universe transitioned from a dark, neutral state to the vibrant, ionized cosmos we know today. As we move forward, we'll explore another fascinating chapter in the universe's history, the hierarchical model of galaxy formation, where small structures merged over time to create the grand galaxies we see today. Now, let's shift our gaze to a process that shaped the universe on a grand-scale hierarchical galaxy formation. Imagine the early universe as a cosmic construction site, where small building blocks gradually came together to create the magnificent galaxies we see today. This theory, known as hierarchical galaxy formation, suggests that the universe didn't start with massive galaxies fully formed. Instead, it began with tiny structures, small clumps of gas and dark matter, that merged and grew over billions of years. In the early universe, gravity was the master architect. It pulled together these small clumps of matter, causing them to collide and merge. Over time, these mergers created larger and more complex structures. Think of it like a cosmic puzzle where small pieces gradually fit together to form a bigger picture. These early structures, often referred to as proto-galaxies, were the seeds from which modern galaxies grew. One of the key pieces of evidence supporting this theory comes from observations of the early universe. Astronomers have found that smaller galaxies were much more common in the distant past, while larger galaxies became more prevalent as the universe aged. This aligns perfectly with the idea that galaxies grew hierarchically, starting small and merging over time. It's like watching a family tree grow, with smaller branches eventually coming together to form a larger, more intricate structure. But hierarchical galaxy formation isn't just about size, it's also about complexity. As galaxies merged, they didn't just grow bigger, they also became more diverse. Some galaxies evolved into spirals with their iconic swirling arms, while others became ellipticals with their smooth, rounded shapes. These differences were shaped by the unique conditions of each merger, such as the angle of collision, the amount of gas involved, and the presence of dark matter. This process wasn't quick or simple. It took billions of years for galaxies to grow and evolve through countless mergers. Each collision brought new challenges and opportunities, reshaping the galaxies in ways that are still being studied today. For example, when two spiral galaxies merge, they can create a new elliptical galaxy with stars scattered in all directions. These mergers also triggered bursts of star formation, as the collision compressed gas clouds and ignited the birth of new stars. The hierarchical model doesn't just explain how galaxies form. It also helps us understand the large-scale structure of the universe. Galaxies aren't scattered randomly. they are organized into clusters, filaments, and voids, forming a cosmic web. This structure emerged as galaxies grew and merged, with gravity pulling them into these intricate patterns. It's a testament to the power of gravity and the slow, steady process of cosmic evolution. As we continue our journey through the universe's history, we'll explore another fascinating force that shaped the first galaxies, cold dark matter, and its mysterious role in the cosmos. Now, let's turn our attention to one of the most mysterious and influential forces in the cosmos, cold dark matter. While we can't see it directly, its presence is felt everywhere, shaping the universe in ways that are both profound and subtle. Cold dark matter played a crucial role in the formation of the first galaxies, acting as the invisible scaffolding that held everything together. In the early universe, ordinary matter, the stuff we can see like gas and dust, wasn't enough to create the structures we observe today. That's where cold dark matter comes in. Unlike ordinary matter, cold dark matter doesn't interact with light or other forms of electromagnetic radiation. It's invisible, but it has mass, and that mass exerts a gravitational pull. This gravitational force was the key to clumping matter together in the early universe. Imagine the universe shortly after the Big Bang, filled with a chaotic soup of particles. Ordinary matter was too hot and energetic to form stable structures on its own. But cold dark matter, being unaffected by heat and radiation, was able to start clumping together much earlier. These clumps of dark matter acted like gravitational anchors, pulling in surrounding gas and dust. Over time, these regions of higher density grew, forming the seeds of the first galaxies. One of the most fascinating aspects of cold dark matter is how it influenced the large-scale structure of the universe. Because it doesn't interact with light, dark matter could form vast, invisible networks, cosmic filaments that stretched across the universe. These filaments became the backbone of the cosmic web, guiding the flow of ordinary matter and shaping the distribution of galaxies. Without cold dark matter, the universe might have remained a diffuse, featureless expanse. But cold dark matter didn't just provide the gravitational glue for galaxy formation, it also influenced the way galaxies evolved. As galaxies grew, the dark matter surrounding them created halos, massive spheres of invisible matter that extended far beyond the visible edges of the galaxies. These halos played a critical role in regulating the growth of galaxies, controlling the flow of gas and influencing the formation of stars. The evidence for cold dark matter comes from a variety of sources. Observations of galaxy rotation curves, for example, show that stars on the outer edges of galaxies move faster than they should if only visible matter were present. This suggests the presence of additional, unseen mass dark matter. Similarly, gravitational lensing, where light from distant objects is bent by the gravity of massive structures, provides further proof of dark matter's existence. As we continue to explore the mysteries of the early universe, cold dark matter remains a central piece of the puzzle. Its role in galaxy formation is undeniable, yet it continues to challenge our understanding of the cosmos. What exactly is dark matter made of? How does it interact with the rest of the universe? These are questions that scientists are still working to answer, and each discovery brings us closer to unraveling the secrets of the universe's first galaxies. Next, we'll explore a contrasting idea: warm dark matter, and how it might offer a different perspective on the formation of the cosmos. Now, let's shift our focus to a fascinating alternative to cold dark matter: warm dark matter. While cold dark matter is often seen as the dominant force in shaping the early universe, warm dark matter offers a different perspective, suggesting that lighter particles may have played a significant role in the formation of the first galaxies. Unlike cold dark matter, which is thought to consist of slow-moving, heavy particles, warm dark matter is made up of lighter, faster-moving particles. These particles would have moved more freely through the early universe, creating a smoother distribution of matter. This difference in behavior could have had a profound impact on how galaxies formed. In the warm dark matter scenario, the lighter particles would have been less effective at forming the small, dense clumps that cold dark matter created. Instead, they would have produced larger, more diffuse structures. This means that the first galaxies might have formed later and been fewer in number compared to the cold dark matter model. However, these galaxies could have been more massive, as the larger structures allowed more matter to accumulate in one place. One of the key implications of warm dark matter is its effect on the cosmic web, the vast network of filaments that connects galaxies across the universe. In this model, the filaments would be thicker and less dense, with fewer small-scale structures. This could explain why some regions of the universe appear to have fewer dwarf galaxies than predicted by the cold dark matter theory. Another interesting aspect of warm dark matter is its potential to solve some of the puzzles that cold dark matter leaves unanswered. For example, the cold dark matter model predicts the existence of many small satellite galaxies around larger ones, but observations have found fewer than expected. Warm dark matter, with its smoother distribution, could naturally account for this discrepancy by suppressing the formation of these smaller structures. However, warm dark matter isn't without its challenges. One of the main criticisms is that it struggles to explain the rapid formation of large galaxies in the early universe. If warm dark matter particles were moving too quickly, they might not have had enough time to clump together and form the massive structures we observe today. This has led some scientists to propose hybrid models, combining elements of both cold and warm dark matter to better match observations. The debate between cold and warm dark matter highlights the complexity of understanding the universe's first galaxies. While cold dark matter remains the leading theory, warm dark matter offers a compelling alternative that could help us refine our understanding of the cosmos. As we continue to study the early universe, the interplay between these two ideas will undoubtedly shed more light on the mysteries of galaxy formation. Next, we'll explore another pivotal force in the early universe, cosmic inflation, and how it set the stage for the birth of galaxies. Now, let's turn our attention to one of the most groundbreaking ideas in modern cosmology, cosmic inflation. This theory proposes that in the earliest moments of the universe, space itself underwent an incredibly rapid expansion, stretching faster than the speed of light. This explosive growth didn't just set the stage for the Big Bang, it also laid the groundwork for the formation of galaxies. Imagine the universe as a tiny, dense seed. In a fraction of a second, cosmic inflation caused that seed to expand exponentially, smoothing out irregularities and creating the vast, uniform expanse we see today. But here's the fascinating part. This rapid expansion didn't just stretch space, it also amplified tiny quantum fluctuations. These fluctuations, initially no larger than subatomic particles, were stretched to cosmic scales, becoming the seeds for the large-scale structure of the universe. These seeds eventually grew into the cosmic web, the intricate network of galaxies, clusters, and voids that define the universe's architecture. Without cosmic inflation, the universe might have remained a chaotic, uneven mess, making the formation of galaxies as we know them nearly impossible. Instead, inflation provided the perfect conditions for gravity to take over, pulling matter together into the first galaxies. One of the most compelling pieces of evidence for cosmic inflation comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation shows tiny temperature variations that match the predictions of inflation theory, offering a snapshot of the universe just moments after its rapid expansion. These variations are like cosmic fingerprints, revealing the initial conditions that led to the formation of galaxies billions of years later. But cosmic inflation isn't just about explaining the past, it also has profound implications for the future of our universe. By understanding how inflation shaped the early universe, we gain insights into the forces that continue to drive its evolution. It's a reminder that the story of galaxy formation is deeply intertwined with the very fabric of space and time. As we move forward, we'll explore another key player in the cosmic drama: supermassive black holes and their role in shaping the first galaxies. Stay tuned, because the mysteries of the universe are far from over. Now, let's shift our focus to one of the most enigmatic and powerful forces in the cosmos: supermassive black holes. These colossal objects, often found at the heart of galaxies, are not just destructive voids. They played a pivotal role in shaping the first galaxies and their evolution. Picture this: in the early universe, as the first galaxies began to form, supermassive black holes were already lurking in their centers. These black holes, with masses millions or even billions of times greater than our Sun, exerted an immense gravitational pull. This pull didn't just trap matter, it also influenced the surrounding gas and stars, shaping the very structure of the galaxy itself. One of the key ways supermassive black holes impacted galaxy formation was through their ability to regulate star formation. As gas and dust fell toward the black hole, they formed a swirling disk of material called an accretion disk. This disk heated up to incredible temperatures, emitting vast amounts of energy in the form of radiation and powerful jets. These jets could blow away surrounding gas, preventing it from collapsing to form new stars. In this way, supermassive black holes acted as cosmic regulators, controlling the growth of their host galaxies. But that's not all. Supermassive black holes also played a role in the growth of galaxies through mergers. When two galaxies collided, their central black holes would eventually spiral toward each other, merging into an even larger black hole. This process released gravitational waves and enormous amounts of energy, which could trigger bursts of star formation and reshape the galaxy's structure. Interestingly, the relationship between supermassive black holes and their host galaxies is so intertwined that astronomers have observed a correlation between the mass of a black hole and the size of its galaxy. This suggests that black holes and galaxies grew together, influencing each other's evolution over billions of years. The presence of supermassive black holes in the early universe also provides clues about how galaxies formed so quickly after the Big Bang. Some theories suggest that these black holes may have formed from the collapse of massive gas clouds or the remnants of the first stars. Once formed, they acted as gravitational anchors, pulling in matter and helping to build the galaxies we see today. As we continue to explore the mysteries of the early universe, supermassive black holes remain a fascinating piece of the puzzle. Their influence on galaxy formation and evolution highlights the intricate balance of forces that shape the cosmos. Next, we'll dive into another critical factor in the story of the first galaxy's: feedback from supernova. Stay with us, as the journey through the universe's origins is just getting started. Now, let's turn our attention to the explosive powerhouses of the early universe: supernova. These cataclysmic events, marking the violent deaths of the first stars, were not just dramatic endings, they were also the birthplaces of the building blocks for future galaxies. When the first stars, known as population 3 stars, reached the end of their lives, they didn't fade quietly. Instead, they exploded in spectacular supernova, releasing enormous amounts of energy and scattering their material across vast regions of space. This material wasn't just ordinary gas, it was enriched with heavy elements like carbon, oxygen, and iron, forged in the hearts of these stars during their lifetimes. These heavy elements, often referred to as metals in astronomy, were crucial for the formation of future galaxies. Before supernova, the universe was composed mostly of hydrogen and helium, the simplest elements created during the Big Bang. But as supernova erupted, they seeded the surrounding gas clouds with these heavier elements. This enrichment process transformed the chemistry of the cosmos, making it possible for more complex structures like planets and life to eventually form. The feedback from supernova also played a dynamic role in shaping the early universe. The shock waves from these explosions compressed nearby gas clouds, triggering the collapse of new star-forming regions. At the same time, the energy released by supernova could also blow gas away from certain areas, preventing further star formation. This delicate balance between triggering and suppressing star formation helped regulate the growth of early galaxies, ensuring they didn't grow too quickly or too slowly. Interestingly, the heavy elements ejected by supernova didn't just stay in one place. Over time, they mixed with the surrounding gas, creating a more diverse and enriched interstellar medium. This enriched gas eventually coalesced into the second generation of stars, which were different from their predecessors. These new stars had a richer chemical makeup, allowing for the formation of rocky planets and eventually the complex chemistry necessary for life. The legacy of supernova extends far beyond their explosive deaths. By enriching the universe with heavy elements and influencing the formation of new stars and galaxies, they laid the groundwork for the cosmos as we know it today. Without these cosmic explosions, the universe would have remained a much simpler and less dynamic place. As we continue to explore the origins of the first galaxies, the role of supernova stands out as a key piece of the puzzle. Their explosive feedback not only shaped the early universe, but also set the stage for the rich diversity of structures we see today. Next, we'll delve into another fascinating aspect of galaxy formation, galaxy mergers. Stay tuned as the story of the universe's first galaxies continues to unfold. Now, let's shift our gaze to another dramatic chapter in the story of the early universe galaxy mergers. Imagine two massive galaxies, each containing billions of stars, hurtling toward each other in a cosmic dance. These collisions weren't rare events in the early universe. In fact, they were a fundamental part of how galaxies grew and evolved. When galaxies merged, it wasn't just a simple collision. The process was chaotic and transformative. As the galaxies approached each other, their immense gravitational forces began to pull and twist their shapes, stretching stars and gas into long, swirling streams. Over millions of years, these two galaxies would gradually merge into one, creating a new, larger galaxy with a unique structure. One of the most striking outcomes of galaxy mergers was the formation of elliptical galaxies. These galaxies, which lack the spiral arms of their counterparts, are thought to have formed through the violent collisions and mergers of smaller galaxies. The intense gravitational forces during these events disrupted the orderly rotation of stars, leading to the more random, spherical distribution seen in elliptical galaxies. But mergers didn't just change the shape of galaxies, they also fueled bursts of star formation. As the gas clouds within the colliding galaxies were compressed, they triggered the birth of new stars at a rapid pace. These starbursts lit up the early universe, creating some of the brightest galaxies we can observe today. Interestingly, galaxy mergers also played a role in feeding supermassive black holes. As gas and dust were funneled toward the centers of merging galaxies, they provided a feast for the black holes lurking there. This influx of material caused the black holes to grow rapidly and, in some cases, become active galactic nuclei, emitting enormous amounts of energy and light. The impact of galaxy mergers extended far beyond the galaxies involved. These collisions helped shape the large-scale structure of the universe, creating the web-like patterns of galaxies and clusters we see today. Without these mergers, the universe would look very different, smaller, less diverse, and far less dynamic. As we piece together the history of the early universe, galaxy mergers stand out as a key mechanism in the evolution of galaxies. They remind us that the cosmos is not a static place, but a dynamic, ever-changing tapestry of interactions and transformations. Next, we'll explore another fascinating piece of the puzzle: the first quasars, the brightest objects in the early universe. Stay tuned as the story of the universe's first galaxies continues to unfold. Now, let's turn our attention to one of the most dazzling phenomena in the early universe: quasars. These incredibly bright objects, powered by supermassive black holes, played a pivotal role in shaping and illuminating the first galaxies. Picture this: a quasar is like a cosmic lighthouse, beaming intense light across billions of light years, outshining entire galaxies. But what exactly are quasars, and why are they so important to the story of the universe's first galaxies? Quasars are the result of supermassive black holes at the centers of galaxies, feeding on vast amounts of gas and dust. As this material spirals into the black hole, it heats up to extreme temperatures, releasing enormous amounts of energy in the form of light and radiation. This process makes quasars some of the brightest objects in the universe, visible even from incredible distances. In fact, the light from the most distant quasars has traveled for billions of years, giving us a glimpse into the universe's infancy. But quasars weren't just cosmic light shows, they were also key players in the evolution of early galaxies. The intense radiation emitted by quasars had a profound impact on their surroundings. It ionized the surrounding gas, stripping electrons from atoms and creating a hot, charged environment. This process, known as feedback, could either trigger star formation by compressing nearby gas clouds or suppress it by blowing gas away from the galaxy. In this way, quasars helped regulate the growth and structure of the galaxies they inhabited. Another fascinating aspect of quasars is their connection to galaxy formation. Many of the earliest galaxies we observe today are thought to have hosted quasars in their centers. These quasars likely played a role in shaping their host galaxies, influencing the distribution of stars and gas. Some scientists even suggest that quasars may have acted as cosmic seeds, around which galaxies formed and grew. This idea highlights the intricate relationship between supermassive black holes and the galaxies they inhabit. Quasars also provide us with valuable clues about the early universe. Because they are so bright, they serve as beacons, illuminating the gas and dust between galaxies. By studying the light from quasars, astronomers can map the large-scale structure of the universe and learn about the conditions that existed billions of years ago. In a sense, quasars are like time capsules, preserving information about the universe's formative years. As we continue to explore the mysteries of the early universe, quasars stand out as both fascinating objects and crucial tools for understanding galaxy formation. Their brilliance not only lit up the cosmos but also helped shape the galaxies we see today. Next, we'll delve into another intriguing theory: the role of magnetic fields in the formation of the first galaxies. Stay with us as we uncover more secrets of the universe's earliest days. Now, let's shift our focus to a force that's often overlooked but may have played a crucial role in shaping the universe's first galaxies: magnetic fields. While we often think of gravity as the primary driver of galaxy formation, magnetic fields could have been just as influential, quietly shaping the cosmos in ways we're only beginning to understand. Magnetic fields are invisible lines of force that can affect the movement of charged particles like electrons and protons. In the early universe, these fields were likely much weaker than they are today, but even their faint presence could have had a significant impact. Imagine a vast, chaotic sea of gas clouds swirling in the darkness of the early cosmos. As these clouds began to collapse under the pull of gravity, magnetic fields could have acted like cosmic threads, guiding and shaping the flow of gas. One way magnetic fields may have influenced galaxy formation is by regulating the collapse of gas clouds. Without magnetic fields, gas clouds would collapse freely under gravity, forming stars and galaxies in a relatively straightforward manner. But magnetic fields introduce a kind of cosmic resistance, slowing down the collapse and creating more structured, organized systems. This resistance could have allowed gas clouds to fragment into smaller clumps, leading to the formation of stars and eventually galaxies. Another intriguing possibility is that magnetic fields help channel gas into specific regions, creating the dense cores needed for star formation. Think of it like a cosmic funnel, directing gas into the right places at the right times. This process could have been especially important in the early universe, where conditions were far more chaotic than they are today. By providing a kind of cosmic scaffolding, magnetic fields may have helped stabilize gas clouds, making it easier for galaxies to form. But how did these magnetic fields come to exist in the first place? Scientists believe they could have been generated by the motion of charged particles in the early universe, a process known as dynamo action. As these particles moved and collided, they could have created tiny magnetic fields that grew stronger over time. Alternatively, magnetic fields might have been present from the very beginning, imprinted on the universe during its earliest moments. Either way, their influence on galaxy formation is a topic of ongoing research and debate. Magnetic fields also have the potential to explain some of the mysteries we observe in the universe today. For example, they could help us understand why some galaxies have such well-defined spiral arms, or why certain regions of space are filled with turbulent, swirling gas. By studying the role of magnetic fields in the early universe, we can gain new insights into the forces that shape the cosmos as we know it. As we continue to explore the universe's earliest days, magnetic fields remind us that even the smallest forces can have a profound impact. They may not be as flashy as quasars or as mysterious as dark matter, but their subtle influence could have been the key to unlocking the secrets of galaxy formation. Next, we'll turn our attention to another fascinating piece of the puzzle, the first proto-galaxies. Stay with us as we uncover more about the building blocks of the universe. Now, let's journey back to a time when the universe was still in its infancy, a time when the first proto-galaxies began to take shape. These proto-galaxies were the early building blocks of the galaxies we see today, and understanding them is like uncovering the first chapters of the universe's grand story. Proto-galaxies were essentially the seeds of modern galaxies. They formed from the densest regions of gas and dark matter in the early universe, where gravity began to pull matter together into clumps. These clumps were not yet the majestic spiral or elliptical galaxies we're familiar with. They were smaller, messier, and far less organized. Imagine them as cosmic construction sites, bustling with activity but still far from finished. One of the key features of proto-galaxies was their abundance of gas. This gas was mostly hydrogen and helium, the simplest and most abundant elements in the universe. Over time, this gas began to cool and condense, forming the first stars. These stars, in turn, lit up the proto-galaxies, making them some of the earliest sources of light in the universe. But this process wasn't instant. It took millions, even billions, of years for proto-galaxies to evolve into the galaxies we recognize today. As proto-galaxies grew, they began to merge with one another. These mergers were like cosmic collisions, where smaller proto-galaxies combined to form larger structures. This process, known as hierarchical galaxy formation, played a crucial role in shaping the universe. Each merger added more gas, stars, and dark matter to the growing galaxy, gradually transforming it into the complex systems we observe today. But proto-galaxies weren't just passive collections of gas and stars. They were dynamic and ever-changing. The first stars that formed within them were massive and short-lived, ending their lives in spectacular supernovae. These explosions enriched the surrounding gas with heavier elements like carbon, oxygen, and iron, which would later become the building blocks of planets and life. This cycle of star formation, death, and enrichment was a key driver of galaxy evolution. Another fascinating aspect of proto-galaxies is their connection to the cosmic web. This vast network of dark matter filaments acted like a cosmic highway, guiding the flow of gas and the formation of galaxies. Proto-galaxies formed at the intersections of these filaments, where the density of matter was highest. Over time, gravity pulled these proto-galaxies closer together, leading to the formation of galaxy clusters and superclusters. Studying proto-galaxies is like looking through a cosmic time machine. By observing the most distant galaxies, astronomers can catch glimpses of these early structures and piece together how they evolved. Telescopes like the James Webb Space Telescope are particularly well suited for this task, as they can peer back in time to the universe's earliest days. As we continue to explore the universe's origins, proto-galaxies remind us of the incredible journey that led to the galaxies we see today. They were the first steps in a process that spanned billions of years, shaping the cosmos into the intricate and beautiful tapestry we now observe. Next, we'll dive into the cosmic web, the vast network that connected these early galaxies and laid the foundation for the universe's large-scale structure. Stay with us as we unravel more mysteries of the cosmos. Now, let's shift our focus to one of the most fascinating frameworks in cosmology, the cosmic web. Picture the universe not as a random scattering of galaxies, but as an intricate network, a vast tapestry woven together by invisible threads of dark matter. This is the cosmic web, the backbone of the universe's large-scale structure. At its core, the cosmic web is made up of filaments, long, thin strands of dark matter that stretch across the cosmos like the veins of a leaf. These filaments connect at dense nodes where galaxies and galaxy clusters form, creating a web-like pattern that spans billions of light years. It's within these filaments and nodes that the first galaxies began to take shape, guided by the gravitational pull of dark matter. But how did this cosmic web come to be? It all traces back to the early universe just moments after the Big Bang. Tiny fluctuations in the density of matter, amplified by gravity, began to grow over time. Dark matter, which makes up about 85% of the universe's total matter, played a crucial role. Its gravitational influence caused these fluctuations to collapse into filaments, forming the skeleton of the cosmic web. As the universe expanded, ordinary matter, hydrogen and helium gas flowed along these dark matter filaments, pooling at the intersections. These dense regions became the birthplaces of the first galaxies. Over billions of years, gravity continued to pull matter together, causing galaxies to form and cluster along the filaments, while vast voids, regions with little to no matter, remained between them. The cosmic web isn't just a static structure, it's dynamic and ever-evolving. Galaxies move along the filaments, drawn toward the densest nodes by gravity. These nodes, often home to massive galaxy clusters, act as cosmic hubs where galaxies collide, merge, and grow. This continuous flow of matter along the web shapes the universe on the largest scales, creating the stunning patterns we observe today. One of the most remarkable aspects of the cosmic web is how it connects the universe's past to its present. By studying the distribution of galaxies and the structure of the web, astronomers can trace the history of cosmic evolution. Telescopes like the Hubble and the James Webb Space Telescope have allowed us to map this vast network, revealing its intricate details and confirming predictions made by theoretical models. The cosmic web also helps us understand the role of dark energy, the mysterious force driving the universe's accelerated expansion. As dark energy pushes galaxies apart, it stretches the filaments of the cosmic web, altering its structure over time. This interplay between dark matter, dark energy, and ordinary matter continues to shape the universe, influencing how galaxies form and evolve. In many ways, the cosmic web is a testament to the universe's interconnectedness. It shows us that galaxies aren't isolated islands in space, but part of a grand, interconnected network. This web not only shaped the first galaxies, but continues to influence the cosmos today, guiding the flow of matter and the formation of new structures. As we explore the cosmic web, we gain a deeper appreciation for the universe's complexity and beauty. It's a reminder that even on the largest scales, the cosmos is governed by the same fundamental forces that shape our everyday world. Next, we'll turn our attention to the role of radiation in the early universe and how it influenced the formation of the first galaxies. Stay with us as we continue to unravel the mysteries of the cosmos. Now, let's turn our attention to a force that shaped the early universe in ways both subtle and profound: radiation. In the cosmic dance of galaxy formation, radiation played a dual role, acting as both a sculptor and a disruptor. To understand its impact, we need to go back to a time when the first stars ignited, flooding the universe with light and energy. When the first stars, known as population 3 stars, burst into existence, they didn't just illuminate the cosmos, they transformed it. These stars were incredibly massive and hot, emitting intense ultraviolet radiation. This radiation had a profound effect on the surrounding gas, the very material from which future galaxies would form. In some cases, it acted as a catalyst, heating the gas and causing it to collapse under gravity, which helped trigger the birth of new stars and galaxies. In other instances, however, radiation could be destructive, ionizing the gas and blowing it away, effectively halting star formation in certain regions. This process, known as radiative feedback, created a delicate balance. On one hand, radiation from the first stars and galaxies could compress gas clouds, making them denser and more likely to collapse into stars. On the other hand, it could also strip gas away from smaller protogalaxies, preventing them from growing. This push and pull dynamic meant that radiation didn't just passively exist in the early universe, it actively shaped the fate of galaxies. One of the most significant effects of radiation was its role in the epoch of reionization. During this period, the universe transitioned from being filled with neutral hydrogen to becoming ionized, as radiation from the first stars and galaxies broke apart hydrogen atoms into protons and electrons. This process not only cleared the cosmic fog, making the universe transparent to light, but also influenced how and where galaxies could form. Regions that were ionized early on often saw slower galaxy formation, as the gas was too hot and diffused to collapse easily. Meanwhile, areas shielded from radiation remained cooler and denser, allowing galaxies to form more readily. Radiation also played a key role in regulating the growth of galaxies over time. In the early universe, smaller galaxies were particularly vulnerable to the effects of radiation. Their weaker gravitational pull made it easier for radiation to blow away their gas, stunting their growth. Larger galaxies, however, could hold onto their gas more effectively, allowing them to continue forming stars and growing in size. This difference in vulnerability helped create the diverse range of galaxy sizes and shapes we see today. Interestingly, radiation didn't just come from stars. Supermassive black holes at the centers of early galaxies also emitted powerful radiation, often in the form of jets and quasars. These energetic outbursts could heat surrounding gas to extreme temperatures, preventing it from cooling and collapsing into stars. In some cases, this feedback mechanism even shut down star formation entirely, creating galaxies that were massive but devoid of new stars. The interplay between radiation and gas in the early universe was a complex and dynamic process, one that continues to shape our understanding of galaxy formation. By studying the effects of radiation, astronomers can piece together how the first galaxies emerged and evolved, revealing the intricate balance of forces that govern the cosmos. As we move forward, we'll explore another fascinating aspect of the early universe, the first dwarf galaxies. These small but mighty structures played a crucial role in building the galaxies we see today. Stay with us as we continue to uncover the secrets of the universe's first galaxies. Now, let's shift our focus to the smallest yet incredibly significant players in the early universe, the first dwarf galaxies. These tiny cosmic structures, though modest in size, were the building blocks of the grand galaxies we see today. To understand their importance, we need to step back to a time when the universe was still in its infancy, filled with the seeds of what would become the vast cosmic web. Dwarf galaxies are thought to have been among the first structures to form after the Big Bang. Unlike the massive spiral or elliptical galaxies we're familiar with, dwarf galaxies were small, containing only a few billion stars compared to the hundreds of billions found in larger galaxies. But don't let their size fool you. These galaxies were crucial in shaping the universe as we know it. Their small size made them more susceptible to the forces at play in the early universe, such as radiation and gravitational interactions, which influenced their evolution and eventual fate. One of the key ideas about dwarf galaxies is that they served as the foundation for larger structures. Over billions of years, these small galaxies collided and merged, their stars and gas combining to form bigger and more complex galaxies. This process, known as hierarchical galaxy formation, suggests that the universe's largest galaxies didn't form all at once but grew gradually through the merging of smaller ones. Think of it like building a cosmic puzzle. Each dwarf galaxy was a piece that, when combined with others, created the intricate structures we observe today. But why were dwarf galaxies so common in the early universe? The answer lies in the conditions of the cosmos at that time. The universe was much denser, and pockets of dark matter and gas were more evenly distributed. These pockets, under the influence of gravity, collapsed to form small, isolated galaxies. Because they formed early, dwarf galaxies had the advantage of being relatively pristine, composed mostly of hydrogen and helium, the elements forged in the Big Bang. This simplicity made them ideal laboratories for studying the earliest stages of galaxy formation. However, life wasn't easy for these small galaxies. Their low mass meant they had weaker gravitational pulls, making them vulnerable to external forces. Radiation from nearby stars and galaxies could strip away their gas, halting star formation and stunting their growth. Additionally, interactions with larger galaxies often led to their absorption, as they were pulled in and assimilated into more massive structures. Despite these challenges, dwarf galaxies played a vital role in enriching the universe with heavier elements, as their stars produced and dispersed elements like carbon, oxygen, and iron through supernovae. Interestingly, some dwarf galaxies managed to survive to the present day. These fossil galaxies, found in the outskirts of larger galaxies or in isolated regions of space, offer a glimpse into the early universe. By studying them, astronomers can piece together the conditions and processes that shaped the first galaxies. For example, the Milky Way's satellite galaxies, such as the Large and Small Magellanic Clouds, are modern-day dwarf galaxies that provide valuable insights into the hierarchical growth of galaxies. The story of dwarf galaxies is one of resilience and transformation. Though small, they were instrumental in building the universe's larger structures, acting as the cosmic equivalent of stepping stones. Their legacy lives on in the galaxies we see today, a testament to the dynamic and interconnected nature of the cosmos. As we continue our journey through the mysteries of the universe's first galaxies, we'll next explore the role of dark energy, a mysterious force that has shaped the expansion of the universe and influenced the formation of galaxies in profound ways. Stay with us as we uncover more secrets of the cosmos. Now, let's turn our attention to one of the most enigmatic forces in the cosmos, dark energy. This mysterious energy, which makes up about 68% of the universe, has been shaping the fate of galaxies since the earliest moments of existence. To understand its role, we need to rewind to a time when the first galaxies were just beginning to form, and the universe was a very different place. Dark energy is the force responsible for the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy works in the opposite direction, pushing galaxies apart. This might sound counterintuitive when thinking about galaxy formation, but its influence is profound. In the early universe, dark energy was less dominant compared to gravity and radiation. However, as the universe expanded and matter spread out, dark energy began to take over, altering the way galaxies formed and evolved. One of the key ways dark energy influenced early galaxies was by shaping the large-scale structure of the universe. As dark energy caused the universe to expand faster, it created more space between galaxies, making it harder for them to interact and merge. This meant that while smaller galaxies could still form, the process of building larger galaxies through mergers became less efficient over time. Think of it like trying to build a sandcastle while the tide is rising. Dark energy made it increasingly difficult for galaxies to come together and grow. But dark energy didn't just affect the spacing of galaxies, it also influenced their internal dynamics. As the universe expanded, the gravitational pull between galaxies weakened, slowing down the rate at which gas could collapse to form stars. This meant that star formation in early galaxies was directly impacted by the presence of dark energy. In some cases, galaxies that might have grown larger and brighter were instead left smaller and dimmer, their potential stifled by the relentless push of dark energy. Interestingly, dark energy also played a role in determining the distribution of galaxies across the cosmos. As it accelerated the expansion of the universe, it created vast voids between clusters of galaxies, regions where matter is sparse and galaxies are few and far between. These cosmic voids are a direct result of dark energy's influence, and they provide astronomers with clues about how the universe has evolved over billions of years. By studying these voids, scientists can better understand the balance between dark energy and other forces in the cosmos. Despite its name, dark energy isn't something we can see or touch. It's a property of space itself, a kind of energy that permeates the universe and drives its expansion. Yet, its effects are everywhere, from the largest structures in the cosmos to the smallest details of galaxy formation. Without dark energy, the universe would look very different. Galaxies would be closer together, star formation would be more active, and the cosmic web would be far denser. As we continue to explore the mysteries of the universe's first galaxies, it's clear that dark energy has been a silent but powerful player in their story. Its influence, though subtle, has shaped the cosmos in ways we are only beginning to understand. Next, we'll dive into the formation of the first spiral galaxies, exploring how their unique structures emerged in the early universe. Stay with us as we unravel more secrets of the cosmos. Now, let's shift our gaze to one of the most iconic shapes in the cosmos, the spiral galaxy. These swirling, disc-like structures with their graceful arms and bright centers are not just beautiful to look at, they also hold clues to how the universe's first galaxies evolved. But how did these intricate spirals come to be in the early universe, and what makes them so unique? The formation of the first spiral galaxies is a story of balance and motion. Unlike elliptical galaxies, which are more chaotic and lack a defined structure, spiral galaxies are characterized by their orderly, rotating disks. This rotation is key to their formation. In the early universe, as gas clouds collapsed under gravity, they began to spin. This spinning motion caused the gas to flatten into a disk, much like how pizza dough flattens when spun. Over time, this disk became the foundation of the spiral galaxy. But what about those iconic spiral arms? These arms are not static. They are dynamic regions where stars, gas, and dust are densely packed. They form due to a phenomenon called density waves. Imagine a traffic jam on a highway. Cars slow down and bunch up in certain areas, creating waves of congestion. In a similar way, as stars and gas move through the galaxy, they encounter regions of higher density, causing them to slow down and clump together. This creates the spiral arms we see today. The first spiral galaxies likely formed in environments where mergers were less frequent. In the early universe, frequent collisions between galaxies often disrupted their structures, leading to more chaotic shapes. However, in quieter regions of space where galaxies could evolve without constant interference, the conditions were right for spirals to emerge. These galaxies had the time and stability needed to develop their distinctive disks and arms. Another factor that contributed to the formation of spiral galaxies was the presence of a central bulge. This bulge, often packed with older stars, acts as a gravitational anchor, helping to maintain the galaxy's structure. In the early universe, as gas flowed toward the center of the galaxy, it fueled the growth of this bulge. Over time, the combination of the rotating disk and the central bulge gave rise to the classic spiral shape. Interestingly, the first spiral galaxies may have looked different from the ones we see today. In the early universe, galaxies were smaller and contained less heavy elements which are crucial for star formation. This means that the first spirals might have had fewer stars and less pronounced arms. However, as these galaxies continued to grow and accumulate more gas and dust, their spiral structures became more defined. The study of spiral galaxies also provides insights into the role of dark matter. While we can't see dark matter directly, its gravitational influence is essential for holding galaxies together. In spiral galaxies, dark matter forms a halo around the disk, providing the extra gravity needed to keep the stars and gas in place. Without dark matter, these galaxies might not have been able to maintain their delicate structures. As we piece together the story of the first spiral galaxies, we gain a deeper understanding of how the universe evolved. These galaxies are not just cosmic wonders, they are also windows into the past, revealing the processes that shaped the early cosmos. Next, we'll explore the formation of the first elliptical galaxies, uncovering how rapid star formation and mergers played a role in their creation. Stay tuned as we continue our journey through the mysteries of the universe's first galaxies. Now, let's turn our attention to another fascinating chapter in the story of the universe's first galaxies, the birth of elliptical galaxies. Unlike the graceful spirals we just explored, elliptical galaxies are a different kind of cosmic marvel. These galaxies, with their smooth, oval shapes and lack of defined structure, tell a story of chaos, collisions, and rapid transformation in the early universe. Elliptical galaxies are thought to have formed through a combination of rapid star formation and frequent galaxy mergers. In the early universe, when galaxies were still young and densely packed, collisions were common. When two galaxies collided, their gas clouds were compressed, triggering bursts of intense star formation. This rapid creation of stars used up much of the available gas, leaving behind a galaxy dominated by older stars and little material for new star formation. Over time, these galaxies settled into their elliptical shapes, characterized by their smooth, featureless appearance. One of the key differences between elliptical and spiral galaxies lies in their motion. While spiral galaxies rotate in an orderly fashion, elliptical galaxies are more chaotic. The stars within them move in random directions, creating a sort of cosmic swarm. This lack of rotation is a direct result of the violent mergers that shaped them. When galaxies collide, their orderly motions are disrupted, and the resulting galaxy inherits this chaotic movement. Another factor that contributed to the formation of elliptical galaxies was the environment in which they formed. In the early universe, certain regions of space were denser than others, with galaxies packed closely together. In these crowded environments, collisions were more frequent, leading to the creation of larger, more massive elliptical galaxies. These galaxies often became the central hubs of galaxy clusters, dominating their surroundings with their immense gravitational pull. Interestingly, elliptical galaxies are also home to some of the oldest stars in the universe. Because they formed so early and used up their gas quickly, the stars within them have had billions of years to age. This makes elliptical galaxies a treasure trove for astronomers studying the early universe. By observing these ancient stars, we can learn more about the conditions that existed when the first galaxies were forming. The role of supermassive black holes in elliptical galaxies is another intriguing aspect of their formation. Many elliptical galaxies contain supermassive black holes at their centers, which may have played a role in shaping their evolution. During galaxy collisions, these black holes could have grown in size, releasing enormous amounts of energy that heated up the surrounding gas and prevented further star formation. This process, known as feedback, helped to maintain the elliptical shape of these galaxies over billions of years. As we explore the origins of elliptical galaxies, we gain a deeper appreciation for the dynamic and often violent processes that shaped the early universe. These galaxies are not just relics of the past, They are living records of the cosmic collisions and transformations that defined the universe's formative years. Next, we'll delve into the role of cosmic dust in the formation of the first galaxies, uncovering how this seemingly insignificant material played a crucial role in shaping the cosmos. Stay with us as we continue to unravel the mysteries of the universe's earliest structures. Now, let's shift our focus to a seemingly humble yet incredibly important player in the story of the universe's first galaxies, cosmic dust. While it might not seem like much at first glance, this tiny, gritty material played a pivotal role in shaping the cosmos as we know it. Cosmic dust created by the first stars was more than just space debris. It was a key ingredient in the recipe for galaxy formation. When the first stars ignited, they didn't just light up the universe, they also forged the building blocks of cosmic dust. These stars, massive and short-lived, ended their lives in spectacular supernova explosions. In their final moments, they ejected heavy elements like carbon, silicon, and iron into space. These elements, along with other materials, clumped together to form tiny grains of dust. Over time, this dust spread throughout the universe, mingling with the vast clouds of gas that filled the early cosmos. But what exactly did this dust do? One of its most critical roles was cooling gas clouds. In the early universe, gas clouds were incredibly hot, making it difficult for them to collapse and form stars. Cosmic dust acted like a cosmic air conditioner, absorbing heat and radiating it away. As the gas cooled, it became denser, allowing gravity to pull it together more effectively. This cooling process was essential for the formation of stars and, ultimately, galaxies. Without cosmic dust, the gas clouds might have remained too hot and diffused to collapse. The dust provided the necessary conditions for gravity to take over, triggering the birth of new stars and the growth of galaxies. In this way, cosmic dust acted as a catalyst, speeding up the process of galaxy formation and helping to shape the large-scale structure of the universe. Another fascinating aspect of cosmic dust is its ability to shield young stars and galaxies from harmful radiation. In the early universe, intense ultraviolet light from the first stars and quasars could have torn apart gas clouds before they had a chance to form stars. Cosmic dust absorbed much of this radiation, protecting the delicate process of star formation and allowing galaxies to grow and evolve. Interestingly, cosmic dust also played a role in the formation of planets. The same dust grains that helped cool gas clouds and form stars eventually became the building blocks of planets, moons, and other celestial bodies. In a way, cosmic dust is not just a relic of the early universe, it's a part of us too. The atoms in our bodies were once part of those ancient dust grains, forged in the hearts of the first stars. As we explore the role of cosmic dust, we begin to see how even the smallest components of the universe can have a profound impact. This seemingly insignificant material was a key player in the formation of galaxies, stars, and planets, shaping the cosmos in ways that continue to influence us today. Next, we'll uncover the story of the first star clusters and how they served as the building blocks for larger galactic structures. Stay with us as we continue to piece together the incredible story of the universe's first galaxies. Now, let's turn our attention to the first star clusters, the cosmic pioneers that laid the groundwork for the galaxies we see today. These clusters, dense groups of stars bound together by gravity, are thought to have formed even before the first galaxies took shape. They were like the seeds from which the vast structures of the universe eventually grew. Imagine the early universe as a vast, chaotic sea of gas and dust. Within this sea, small pockets of material began to clump together, pulled by gravity. These clumps grew denser and hotter until finally the first stars ignited. But these stars didn't form in isolation, they formed in groups, creating the first star clusters. These clusters were the universe's earliest attempts at organization, bringing order to the chaos. One of the key reasons star clusters formed before galaxies is their simplicity. Galaxies are incredibly complex, with intricate structures like spiral arms, bulges, and halos. Star clusters, on the other hand, are relatively straightforward, just a group of stars orbiting a common center. This simplicity made them easier to form in the early universe, where conditions were still settling down after the Big Bang. These early star clusters played a crucial role in the formation of galaxies. As more stars formed within a cluster, their combined gravity began to attract nearby gas and dust. Over time, these clusters grew larger and more massive, eventually merging with other clusters to form the first protogalaxies. In this way, star clusters acted as the building blocks of galaxies, piecing together the larger structures we see today. But star clusters didn't just contribute to the growth of galaxies, they also influenced their evolution. The intense radiation and stellar winds from the stars within these clusters helped shape the surrounding gas, triggering further star formation and driving the growth of galaxies. In a sense, star clusters were like cosmic nurseries, nurturing the birth of new stars and galaxies. Interestingly, some of these ancient star clusters still exist today. Known as globular clusters, they are dense, spherical groups of stars that orbit galaxies like our Milky Way. These clusters are like fossils from the early universe, offering us a glimpse into the conditions that existed billions of years ago. By studying them, astronomers can piece together the story of how the first galaxies formed and evolved. As we explore the role of star clusters, we begin to see how even the smallest structures in the universe played a part in shaping the cosmos. These clusters were the first steps in the journey from chaos to order, from a sea of gas and dust to the intricate galaxies we see today. Next, we'll delve into the role of neutrinos, nearly massless particles that may have influenced the formation of the first galaxies. Stay with us as we continue to unravel the mysteries of the universe's earliest days. Now, shifting our focus to the tiniest yet most intriguing players in the cosmos, let's explore the role of neutrinos in the formation of the first galaxies. Neutrinos are nearly massless particles that zip through the universe at incredible speeds, barely interacting with matter. Despite their elusive nature, these particles might have played a surprisingly significant role in shaping the early universe. In the chaotic aftermath of the Big Bang, neutrinos were among the first particles to emerge. They flooded the universe, moving freely through the dense, hot soup of matter and energy. Because they interact so weakly with other particles, neutrinos could travel vast distances without being slowed down or absorbed. This unique property allowed them to influence the distribution of matter in ways that are still being unraveled by scientists today. One of the key ways neutrinos might have impacted galaxy formation is through their gravitational effects. Even though they are nearly massless, the sheer number of neutrinos in the early universe meant their combined gravity could have subtly influenced the clumping of matter. This gravitational nudge could have helped shape the initial seeds of structure, guiding the formation of the first gas clouds and star clusters that eventually grew into galaxies. Another fascinating aspect of neutrinos is their ability to carry energy away from dense regions of the early universe. As they streamed out of these areas, they could have cooled the surrounding gas, making it easier for gravity to pull matter together. This cooling effect might have accelerated the collapse of gas clouds, speeding up the birth of the first stars and galaxies. However, neutrinos also present a challenge to our understanding of galaxy formation. Because they move so quickly, they tend to smooth out small-scale structures, potentially delaying the formation of smaller galaxies. This phenomenon, known as free streaming, means that neutrinos could have acted as a balancing force, preventing matter from clumping too quickly in certain regions while allowing larger structures to form over time. Today, scientists study neutrinos to better understand their role in the early universe. By observing how these particles behave and interact, researchers can refine their models of galaxy formation and gain new insights into the conditions that existed billions of years ago. Neutrinos may be small and elusive, but their impact on the cosmos could be far greater than we once imagined. As we continue to uncover the mysteries of the universe's first galaxies, neutrinos remind us that even the smallest particles can have a profound influence on the grandest scales. Next, we'll dive into the concept of galactic winds, powerful forces driven by supernova and black holes that shaped the evolution of early galaxies. Stay with us as we journey deeper into the cosmic story. Now, let's turn our attention to the powerful forces that swept through the early universe, galactic winds. These winds, driven by the explosive energy of supernova and the immense gravitational pull of black holes, played a crucial role in shaping the first galaxies. Imagine a cosmic storm, not of rain and thunder, but of gas, dust, and energy, reshaping everything in its path. Galactic winds are essentially streams of charged particles and gas that flow outward from galaxies at incredible speeds. In the early universe, these winds were fueled by the intense activity of young, massive stars. When these stars reached the end of their lives, they exploded as supernova, releasing enormous amounts of energy and ejecting material into space. This material, combined with the radiation from the stars themselves, created powerful outflows that pushed gas and dust away from the galaxy's core. But supernova weren't the only drivers of these winds. Supermassive black holes lurking at the centers of early galaxies also played a significant role. As these black holes consumed matter, they released vast amounts of energy in the form of radiation and jets of particles. This energy could heat up the surrounding gas, driving it outward in powerful winds that could extend far beyond the galaxy itself. These galactic winds had a profound impact on the evolution of early galaxies. By pushing gas and dust out into intergalactic space, they regulated the rate at which new stars could form. In some cases, the winds removed so much material that star formation slowed down significantly, effectively putting a brake on the galaxy's growth. In other cases, the winds enriched the surrounding environment with heavy elements forged in the hearts of stars, setting the stage for future generations of stars and planets. One of the most fascinating aspects of galactic winds is their ability to connect galaxies to the larger cosmic web. As these winds carried material out into the void, they helped distribute elements like carbon, oxygen, and iron across vast distances. This process, known as chemical enrichment, played a key role in shaping the universe's large-scale structure and ensuring that future galaxies had the raw materials needed to form stars, planets, and even life. Today, astronomers study galactic winds by observing distant galaxies and analyzing the light they emit. By studying the signatures of these winds in the spectra of galaxies, scientists can learn more about the conditions in the early universe and the processes that drove galaxy formation. These observations provide valuable insights into how the first galaxies evolved and how they influenced the cosmos we see today. Galactic winds remind us that the universe is a dynamic and interconnected system, where even the smallest events can have far-reaching consequences. Next, we'll explore how tiny quantum fluctuations in the early universe grew into the seeds of galaxy formation, setting the stage for the cosmic structures we observe today. Stay with us as we continue to unravel the mysteries of the universe's first galaxies. Now, let's take a closer look at one of the most mind-bending ideas in cosmology, the role of quantum fluctuations in the birth of galaxies. These tiny, almost imperceptible ripples in the fabric of the early universe may seem insignificant, but they were the starting point for everything we see today. Picture the universe in its earliest moments, a hot, dense soup of energy and particles. At this scale, the rules of quantum mechanics reign supreme, and even the tiniest fluctuations in energy and density could have profound consequences. Quantum fluctuations are essentially random, microscopic variations that occur at the quantum level. In the early universe, these fluctuations were incredibly small, but as the universe expanded during the period of cosmic inflation, they were stretched to enormous scales. What started as tiny ripples became the seeds for the large-scale structure of the cosmos. These fluctuations created regions of slightly higher and lower density, which over billions of years would grow under the influence of gravity. As the universe cooled and matter began to clump together, these density variations became the building blocks for the first galaxies. Areas with slightly more matter attracted even more material, growing denser and hotter until they collapsed under their own gravity, forming stars and galaxies. Meanwhile, regions with less matter remained relatively empty, creating the vast cosmic voids we see today. This process, known as gravitational collapse, was driven by the initial quantum fluctuations that emerged in the universe's first moments. One of the most compelling pieces of evidence for this theory comes from the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation, which fills the entire universe, contains tiny temperature variations that correspond to the density fluctuations from the early universe. These variations match the predictions of quantum mechanics and provide a snapshot of the seeds that would later grow into galaxies and galaxy clusters. The idea that something as small as a quantum fluctuation could lead to the formation of something as vast as a galaxy is both awe-inspiring and humbling. It reminds us that the universe operates on scales far beyond our everyday experience, where the rules of physics can produce outcomes that seem almost magical. These fluctuations not only shaped the first galaxies, but also set the stage for the intricate cosmic web that connects all structures in the universe. As we continue to explore the mysteries of the early universe, quantum fluctuations remain a key piece of the puzzle. They show us how the smallest events can have the largest consequences, shaping the cosmos in ways we are only beginning to understand. Next, we'll delve into how these early structures came together to form the first galaxy clusters, revealing even more about the universe's grand design. Stay with us as we uncover more secrets of the cosmos. Now, let's shift our focus to the next chapter in the story of the universe's first structures, the formation of the earliest galaxy clusters. These massive gatherings of galaxies bound together by gravity are like cosmic cities, and their origins hold vital clues about the early universe. To understand how they came to be, we need to revisit the seeds of structure we've already discussed, those tiny quantum fluctuations that set everything in motion. As the universe expanded and cooled, regions of slightly higher density created by those initial fluctuations began to pull in more matter through gravity. Over time, these denser areas grew into the first galaxies, but gravity didn't stop there. Just as galaxies formed, they began to attract one another, clustering together in groups. These early galaxy clusters were the result of countless smaller structures merging and interacting, creating some of the largest and most complex systems in the cosmos. The process of cluster formation was gradual, taking billions of years. Imagine a cosmic dance where galaxies slowly drift toward one another, drawn by their mutual gravitational pull. As they came together, they formed larger and larger groups, eventually becoming the galaxy clusters we observe today. These clusters are not just random collections of galaxies. They are organized systems, often with a massive elliptical galaxy at their center, surrounded by hundreds or even thousands of smaller galaxies. One of the most fascinating aspects of these early galaxy clusters is what they can tell us about the conditions of the early universe. By studying the distribution and properties of these clusters, scientists can piece together how matter was distributed shortly after the Big Bang. The way galaxies are arranged within clusters, the temperatures of the gas between them, and even the way light bends around these massive structures all provide valuable insights into the universe's history. For example, the hot gas found in galaxy clusters, known as the intracluster medium, emits X-rays that can be detected by telescopes. By analyzing this gas, researchers can measure the cluster's mass and understand how it has evolved over time. Additionally, the way galaxy clusters distort the light from objects behind them, A phenomenon called gravitational lensing allows astronomers to map the distribution of dark matter within these clusters. This, in turn, helps us understand how dark matter influenced the growth of cosmic structures. The first galaxy clusters also serve as cosmic time capsules. Because they are so massive, they retain a record of the universe's early conditions. By studying the oldest and most distant clusters, scientists can peer back in time, uncovering details about the universe's expansion, the role of dark energy, and even the nature of the first stars and galaxies. In many ways, galaxy clusters are like the universe's history books, preserving the story of how everything came to be. They remind us that the cosmos is not just a collection of isolated objects, but a vast, interconnected web of structures, all shaped by the same fundamental forces. As we continue to explore these cosmic giants, we gain a deeper understanding of the universe's origins and its ongoing evolution. Next, we'll turn our attention to the role of baryonic matter, the ordinary matter that makes up stars, planets, and everything we can see, and how it played a crucial part in shaping the first galaxies. Stay with us as we uncover more layers of the universe's grand design. Now, let's take a closer look at the role of baryonic matter, the ordinary stuff that makes up stars, planets, and everything we can see, and how it played a pivotal role in shaping the universe's first galaxies. While dark matter may have provided the gravitational scaffolding for these structures, it was baryonic matter that brought them to life, filling the cosmic stage with light and energy. Baryonic matter, composed of protons, neutrons, and electrons, is the building block of all visible objects in the universe. In the early cosmos, this ordinary matter existed as a hot, dense soup of particles, swirling within the gravitational wells created by dark matter. As the universe expanded and cooled, these particles began to clump together, forming the first atoms of hydrogen and helium. This was a critical moment as it allowed gravity to take hold, pulling these atoms into denser regions and setting the stage for the birth of the first stars and galaxies. But baryonic matter didn't just passively follow the lead of dark matter. It played an active role in shaping the cosmos. For instance, when the first stars ignited, their intense radiation heated the surrounding gas, creating pressure that could counteract gravity. This feedback process regulated how quickly galaxies could form and grow. Additionally, when these early stars died in spectacular supernova explosions, they enriched the surrounding gas with heavier elements like carbon, oxygen, and iron. These elements became the raw materials for future generations of stars, planets, and even life itself. The interaction between baryonic matter and dark matter is a delicate dance. While dark matter's gravity pulls matter together, baryonic matter's ability to radiate energy allows it to cool and condense, forming the dense cores of galaxies. Without this cooling process, galaxies as we know them might never have formed. It's this interplay between the invisible and the visible that makes the story of galaxy formation so fascinating. One of the most intriguing aspects of baryonic matter is how it reveals itself in the universe. For example, the hot gas within galaxy clusters, known as the intracluster medium, is a reservoir of baryonic matter. This gas emits X-rays, allowing astronomers to study its properties and distribution. Similarly, the stars and planets within galaxies are all made of baryonic matter, providing a tangible connection to the processes that shaped the early universe. By studying baryonic matter, scientists can piece together how galaxies evolved over billions of years. They can also explore how this ordinary matter interacts with dark matter, shedding light on one of the greatest mysteries in cosmology. Together, these two forms of matter, visible and invisible, have shaped the universe into the complex, beautiful tapestry we see today. As we continue our journey through the cosmos, we'll explore another fascinating piece of the puzzle, the first starburst galaxies, where star formation reached incredible levels. Stay tuned as we uncover more about these cosmic powerhouses and their role in the universe's grand story. Now, let's turn our attention to a phenomenon that lit up the early universe like a cosmic fireworks display, the first starburst galaxies. These galaxies were unlike anything we see today, experiencing periods of star formation so intense that they reshaped the cosmos around them. Imagine entire galaxies birthing stars at rates hundreds or even thousands of times faster than our own Milky Way. This wasn't just a gentle trickle of starlight, it was a torrent, a flood of new stars bursting into existence all at once. So what caused these starbursts? In the early universe, galaxies were packed with vast reservoirs of gas, the raw material needed to form stars. But it wasn't just the abundance of gas that fueled these starbursts, it was the conditions. Galaxies in the early universe were smaller, denser, and more chaotic than the ones we see today. Collisions between galaxies were common, and these violent encounters triggered shockwaves that compressed gas clouds, igniting rapid star formation. Think of it like striking a match in a room filled with gas. Once the process started, it spread like wildfire. But starbursts weren't just about creating stars, they were also about destruction. The sheer intensity of star formation in these galaxies produced massive stars that burned bright and died young. When these stars exploded as supernovae, they unleashed powerful winds that swept through their host galaxies, blowing gas and dust out into the surrounding space. This feedback process was crucial, as it regulated how much gas remained available for future star formation. In a way, starburst galaxies were both creators and destroyers, shaping their own destinies and the evolution of the universe around them. One of the most fascinating aspects of starburst galaxies is how they influence the cosmic environment. The light from these galaxies traveled across vast distances, ionizing the surrounding hydrogen gas and contributing to the epoch of reionization. This period, when the universe transitioned from being opaque to transparent, was a turning point in cosmic history, and starburst galaxies played a starring role. Their intense radiation helped carve out the first clear paths for light to travel through the universe, paving the way for the cosmos we see today. Today, astronomers study starburst galaxies to understand how the first galaxies formed and evolved. By observing distant starbursts, they can peer back in time to an era when the universe was young and chaotic. These observations provide clues about the conditions that allowed galaxies to grow and change over billions of years. They also help us understand how the elements essential for life, carbon, oxygen, and iron, were forged in the hearts of stars and scattered across the cosmos. As we continue to explore the mysteries of the early universe, starburst galaxies remind us of the incredible dynamism and creativity of the cosmos. They show us that even in its infancy, the universe was a place of extremes where stars were born in dazzling bursts of light and energy. Next, we'll delve into another intriguing theory: the role of cosmic strings in shaping the universe's first galaxies. Stay with us as we uncover more about these cosmic threads and their place in the grand tapestry of the cosmos. Now, let's venture into one of the most speculative yet fascinating ideas in cosmology: the role of cosmic strings in shaping the universe's first galaxies. Cosmic strings are hypothetical one-dimensional defects in space-time, thought to have formed during the early moments of the universe. Imagine them as incredibly thin, incredibly dense threads stretching across the cosmos, remnants of the intense energy fluctuations that occurred just after the Big Bang. While they remain theoretical, their potential influence on galaxy formation is a topic of great interest and debate among scientists. So, how might these cosmic strings have impacted the birth of galaxies? One theory suggests that cosmic strings could have acted as gravitational anchors in the early universe. As these strings moved through space, their immense gravitational pull could have drawn matter toward them, creating dense regions where gas clouds could collapse and form stars. Think of it like a cosmic fishing line, pulling matter together and setting the stage for the first galaxies to emerge. These strings might have served as the scaffolding upon which the universe's large-scale structure was built. Another intriguing possibility is that cosmic strings could have generated ripples in spacetime, much like the waves created by a stone dropped into a pond. These ripples, known as gravitational waves, might have influenced the distribution of matter in the early universe, creating the seeds for galaxy formation. In this scenario, cosmic strings wouldn't just pull matter together, they would also shape the way it clumped and organized itself, leaving a unique imprint on the cosmos. But why are cosmic strings so difficult to detect? For one, they are incredibly thin, with a width smaller than a proton, yet they could stretch across vast cosmic distances. Their energy density is also immense, making them potentially detectable through their gravitational effects. However, despite decades of searching, no direct evidence of cosmic strings has been found. This hasn't stopped scientists from exploring their potential role in the universe's evolution, as their existence could explain some of the mysteries surrounding the distribution of galaxies and the large-scale structure of the cosmos. If cosmic strings do exist, their influence on galaxy formation would have been profound. They could have created the initial conditions for the first galaxies to form, acting as cosmic architects that shaped the universe's structure. While this theory remains speculative, it offers a compelling glimpse into the complex and dynamic processes that might have shaped the early universe. As we continue to explore the cosmos, the search for cosmic strings remains a tantalizing frontier, one that could unlock new insights into the origins of galaxies and the universe itself. Next, we'll explore an even more mind-bending idea: the multiverse and its potential connection to galaxy formation. Could our universe be just one of many, each with its own unique story of galaxy formation? Stay with us as we dive into this cosmic mystery and uncover what it might mean for our understanding of the cosmos. Now, let's take a step beyond our universe and into the realm of the multiverse, a concept that stretches the boundaries of our imagination. The multiverse theory proposes that our universe is just one of countless others, each with its own unique set of physical laws and conditions. This idea, while speculative, offers a fascinating lens through which to explore the diversity of galaxy formation. If multiple universes exist, each could have followed a different path in its evolution, leading to galaxies that look nothing like the ones we see in our own cosmos. So, how might the multiverse influence galaxy formation? In some universes, the fundamental constants like the strength of gravity or the density of dark matter could be vastly different from ours. These variations would dramatically alter how galaxies form and evolve. For instance, in a universe with stronger gravity, galaxies might collapse into dense, compact structures much earlier, while in a universe with weaker gravity, galaxies could take far longer to form if they form at all. The multiverse theory suggests that the galaxies we observe in our universe are just one possible outcome among an infinite array of possibilities. But why does this matter? The multiverse theory could help explain why our universe seems so finely tuned for galaxy formation. If countless universes exist, each with different physical laws, it's possible that only a small fraction of them have the right conditions to support the formation of galaxies like ours. This idea, known as the anthropic principle, suggests that we observe a universe capable of supporting life because, well, we're here to observe it. In other words, the multiverse might be the reason our universe has the perfect recipe for galaxies, stars, and planets. One of the most intriguing aspects of the multiverse theory is its potential to explain the diversity of galaxy shapes and sizes. In our universe, we see everything from spiral galaxies with elegant arms to elliptical galaxies that resemble glowing orbs. If other universes exist, they might host galaxies that defy our current understanding, structures so bizarre and unique that they challenge our very definition of what a galaxy is. The multiverse opens the door to a cosmic zoo of possibilities, where every universe could be home to its own distinct galactic wonders. Of course, the multiverse remains a highly speculative idea, with no direct evidence to confirm its existence. Yet it continues to captivate scientists and enthusiasts alike, offering a bold framework to explore the origins and diversity of galaxies. As we push the boundaries of our knowledge, the multiverse theory reminds us that the cosmos is far more mysterious and vast than we can imagine. And who knows, perhaps one day we'll uncover clues that reveal not just the story of our universe, but the stories of countless others as well. With that, we've reached the end of our journey through 30 theories about the universe's first galaxies. From the Big Bang to cosmic strings, and now the multiverse, each idea offers a unique perspective on how the cosmos came to be. As we continue to explore the mysteries of the universe, one thing is certain: the story of galaxy formation is far from over. What new discoveries await us in the vast expanse of space? Only time will tell. As we wrap up our exploration of the universe's first galaxies, it's clear that the story of their formation is as complex as it is fascinating. From the explosive beginnings of the Big Bang to the intricate dance of dark matter and cosmic inflation, each theory we've discussed offers a unique piece of the puzzle. Whether it's the role of primordial gas clouds, the explosive feedback from supernova, or the speculative wonders of the multiverse, these ideas remind us just how much we still have to learn about the cosmos. The diversity of these theories highlights the incredible creativity and curiosity of scientists who strive to understand the origins of everything we see in the night sky. Yet for every answer we uncover, new questions emerge, deepening the mystery of the universe's first galaxies. What triggered the formation of the first stars? How did tiny quantum fluctuations grow into the vast cosmic web we observe today? And could there be other universes out there, each with its own unique galactic story? As we look to the future, one thing is certain: the journey to understand the universe's first galaxies is far from over. With every new discovery, we inch closer to unraveling the secrets of the cosmos. But for now, the universe remains a place of endless wonder, inviting us to keep exploring, questioning, and imagining. So, what do you think? Which of these theories resonates with you the most? Do you believe we'll one day uncover the full story of how galaxies came to be? Share your thoughts in the comments below. We'd love to hear your perspective. And if you're as captivated by the mysteries of the cosmos as we are, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss out on our next deep dive into the wonders of the universe. Until next time, keep looking up. The stars have so much more to tell us.